after my colleague Yang Leizhou introduced his ISS internal multiple elimination algorithm, here I would like to provide you an alternative ISS internal multiple eliminator for the first order internal multiple generated by the ocean bottom for this specific case. And since this is an initial study, we only discuss this problem in one normal instance case. This work belongs to the developments that are beyond the current ISS internal multiple attenuation algorithm. And to show you what kind of problem we'll address here, I first show you an typical marine environment. And you can see that in this model, beneath the ocean bottom, you have hundreds of layers, including one salt band. So in your seismic data, you can receive this type of internal multiple, which is generated by this ocean bottom. And if we define the transmission coefficients from the first layer to the second layer as the T01 and the T10, as my colleague Yang Leizhou just show you in details of how ISS internal multiple prediction works. Right now, the prediction provided by the attenuation algorithm has difference with the actual internal multiple, and this difference, it can be specified as the T01, T10, which is an attenuation factor. Besides this kind of simple first-order internal multiple, you can also have this kind of internal multiple recorded in your data, and we can see that this multiple event travels much deeper than the first one I showed you. So for this kind of event, it can carry hundreds of transmission coefficient and reflection coefficient. But as long as the internal multiple is downward reflected by the ocean bottom, then the difference between your between your prediction from the attenuation algorithm and the actual internal multiple is T01, T10. So for this certain type of the internal multiple, if you want to eliminate it, our task is to remove the T01, T10 from our prediction. And we want to point out that this kind of factor can be obtained as long as you know the information down to and across this ocean bottom, which means you only need to know the C0 and C1 here, without knowing other properties and actual internal multiple going through. So after we know the difference between our attenuator can give and the actual internal multiple, our group proposed two different approaches to develop an eliminator. The first approach is use the data directly in the inverse scattering series to develop an internal multiple eliminator, as shown by my colleague Yang Leizhou. And he not only shows you how to remove the T01, T10 factor, also for other attenuation factors which generated by all the reflectors. In this part, since we start from the inverse scattering series, utilize the multiplication of data, so we do not need any subsurface information. But in this talk, I would like to provide you an alternative way, which means for a certain circumstances, and there are times where the property down to and across the ocean bottom can be obtained, which means in this case we can use the data, to find the velocity C1 first. Combined with the C0 we have already known, we have the T01, T10 actually is achievable. So in this second approach, we give the algorithm directly give the known T01, T10 directly to the algorithm. See if that can eliminate this for the certain type of internal multiple, which is the first order internal multiple generated by the ocean bottom. And here we provide one approach, but not only the approach, to develop an alternative eliminator. And the idea is pretty simple. Since we assume that we know the velocity from down to and across the ocean bottom, so we can give remove the known T01, T10 in one outer B1 in our algorithm. Instead of using 3 identical B1 as the current internal multiple attenuation algorithm used, this project is inspired by 2 different migration methods. The first one is the phase shift migration method, first proposed by Gastag in 1978. In this kind of migration method, only provide a phase shift for the data and migrate the data to the depth domain without changing the amplitude inside your data. And the second migration method is the stored extended Clarabelle 3 migration method with the WKBG approximation. Different from the phase shift migration method, this migration method not only phase shift your event, but also will change the amplitude of your event by a explicit factor. See, so we use the amplitude change in this C3 WKBG migration, and instead of using 3 identical B1, we substitute one of the outer B1 as the WKBG C3 migration. Keep left two of the B1 as only the phase shift migration without any amplitude change. And we will use the amplitude change in the C3 WKBG migration to remove our target, which is the known T01, T10 factor. Next, let me show you a numerical result, which is performed in 1D normal incidence case. First, let me show you the synthetic data we use. Here is the 1D normal incidence velocity model for our synthetic data generation. We can see that for the first layer, we use the velocity of water, and the second layer, we use a velocity of typical sedimentary layer. So we can treat the first reflector here as the ocean bottom. And beneath the sedimentary layer, we give the salt velocity as the third layer. So we can treat the third layer as a salt band. And beneath that salt band, we have another reflector which contains the velocity a little bit bigger than the salt velocity. This model is arranged here on purpose to produce the interference between the third primary and the first order internal multiple, which is shown in these 3 figures. The left figures here shows you the interference event, and the middle figure here shows you the third primary, and the right figure here shows you the first order internal multiple. We can see that the first order internal multiple, which interferes with the third primary, has a big amplitude with opposite phase compared to our third primary. So these two interfering each other will give us the data as we show in the left hand side here. So we are interested in, can we eliminate this first order internal multiple and retrieve the third primary here. The reason we are interested in this question is this kind of internal multiple is exactly the type that the current SS internal multiple attenuation algorithm plus the adaptive subtraction have difficulty with. So eliminating this kind of internal multiple without damaging a primary is actually beyond the capability of current method. In the later test, we are interested in evaluating the difference between the current attenuator and the eliminator proposed in this presentation can make on this type of internal multiple. We will show you the results soon. Here is the whole trace of the normal incidence, 1D normal incidence data, and the event in this red box here has been shown in the previous slides to which is an interfering event. Okay. Now we have the synthetic data, and we will move to SS internal multiple removal processing. In this processing, since we use two different migration methods here, and we find a smooth velocity profile on purpose, where the purpose is to provide a WKBG amplitude that removes the T01, T10, which is assumed to be known here. And so this designed smooth velocity profile, which is plotted as the right color line here, is an effective velocity profile which turns the current attenuator into an eliminator. And the black line here is the sharp boundary with the velocity C0 and C1. We assume we know that, and we design this smooth velocity. After we apply this smooth velocity profile into these two different migration and predict the internal multiple, we can remove the internal multiple from our data set. Here is the result after the internal multiple removal by using current SS internal multiple attenuation algorithm and the elimination algorithm we just discussed. So we can see that for first two primary events, there is no change, which means our internal multiple prediction does not touch the primary event. So the difference happens on this third event, as we discussed before. It's an interfering event. So next slide, I will show you the large scale of this part, which is in this red box. This solid green line here represents the event interfering by the third primary and the first order internal multiple generated by this ocean bottom. And also we simulated this actual third primary. If the internal multiple can be eliminated from this green line here, then the result should agree with this black line, which is the actual third primary. First, let's take a look at the how the current SS internal multiple attenuation algorithm does. The solid blue line here gives you the SS internal multiple attenuated result with the current method. It's not a bad result. We can see that the internal multiple, the energy of the internal multiple is attenuated, but the residual of this event is still points to the opposite direction compared to the actual primary. So we can see that this event can be attenuated but not eliminated by using current method. After we incorporating this known T01, T10 using the method we just described, then we can see that the internal multiple can be eliminated as shown on this red dash line. The red dash line here is agree with this simulated actual third primary, which means all the internal multiple on this interfering event has been eliminated. So at the last, I would like you to, here are some key points I would like you to take away. First is we add an alternative tour of internal multiple eliminator for the first order internal multiple generated by the ocean bottom, which is a specific case, and which only needs the velocity down to and across the ocean bottom. This we don't require all the properties the internal multiple travels through in its history. And both of these two approaches will be progressed, and we will keep you posted. Thank you.